Now I turn it over to Scott Plant, the structural field engineer for the main span as well as cable. And Scott.
Thank you, Razul. Good morning. My name is Scott Plant, and I was the senior structural field engineer for the project. As you can see in this slide, in the construction of the towers, the maximum elevation of the towers was 272 feet due to its close proximity to Newark Airport. The towers are tapered, as you can see from these dimensions of 17 by 11 at the surface of the footing, and up to 13 by 11 at the strut, and it even thins out a little further as it goes up. This was pretty much for aesthetics and for cost savings on the amount of concrete that was utilized to construct the towers. One of the interesting things about the towers was the survey of them. The survey of them was very important as we constructed each of the 17 lifts, but more importantly, as you went up higher above the strut and to the top of the tower, there were at times when all personnel had to evacuate the formwork where we were forming and placing the tower lifts in order for the surveyors to get accurate readings on that, in order to not only give the tower its taper, but its outward lean. There are 17 lifts from 45 to 110 cubic yards. Obviously, the larger placements were at the top of the footing. And in that particular area at the top of the footing, the rebar came for the towers were number 11 and 14 vertical bars that were embedded in the footing and came out of the footing to start the tower construction. The concrete strut, colored in blue in this slide, is a heavily reinforced and post-tension section that stabilizes the two tower pylons together and supports the bridge deck. The access to the hollow sections above the deck, this gave us in this area there was a series of ladders and platforms with access to each stay cabled anchorage in the tower for future inspection and maintenance. This access was also helpful in the construction of the stay cable system in the towers. The design and construction of the towers was unique in that the ratio of the tower height above the roadway to the main span length was 13.5%. This is currently a world record in stay cable bridges and was due to the close proximity to Newark Liberty Airport. The first step in the construction of the towers was to schedule pre-activity meetings for the major tower construction operations, such as the footings, of which there were 4, the pylons, there were a total of 8, and the concrete strut between the towers, in which there were 4. These meetings were attended by the contractor superintendents and project engineers who performed production and quality control functions. KSC's quality assurance engineers and inspectors were in this meeting, along with Port Authority personnel and their representatives. During this meeting, the specific construction operation was reviewed, soup to nuts, and discussed along with the quality requirements. One of the main quality requirements were checklists. Both the quality control and quality assurance entities developed checklists to document that the specific items in the checklist were completed during the operation to, say, place a tower lake segment. KSC's quality assurance quality controlled inspection checklists were much longer than the contractor's QC checklist and had to be approved by the engineer of record prior to use. Every concrete placement on the project had a rebar, formwork, and concrete controlled inspection checklist. As you would expect, there were numerous concrete placements on the project and therefore hundreds of checklists. A couple of other things I wanted to say about the quality assurance is that all inspectors had to do a daily work report to document their inspections and monitoring of the construction operations. There was a hold point program, and the hold points were designated in the checklist. And these points were mandatory inspections where the inspectors had to be there before anything could proceed further. There were also NCRs, which were the non-conformance reports. So if the contractor performed work that wasn't done properly, a non-conformance report would then be issued for the contractor to respond to with what they planned on doing to rectify the problem. Next slide, please. Obviously, the tower configuration, as we said earlier, was affected by the close proximity to Newark Airport. This configuration had lower towers and longer spans, which I talked about earlier in the first slide. One of the things that I wanted to note was that the towers, they lean outwards 5 degrees, eliminating over the roadway cables and struts, because in the Northeast, with icing conditions in the winter, you do not want the cables or struts above the roadway being in the roadway path, where if you had an icing event, ice could fall down to the cars and the trucks below on the bridge. So that design is unique that you see throughout the colder climate regions in the country. In this slide below, you can see a photograph of the concrete placement of one of the tower footings in the lower left. KSC managed the construction inspection and testing of the footing placement and all other placements with ACI certified concrete construction special inspectors. That was a requirement of the Port Authority that all the inspectors are certified that are involved in concrete. Each of the 4 tower footing placements consisted of 2,000 cubic yards of concrete delivered from 2 different concrete plants. 2 concrete pumps were utilized to place the footing, and 12 inspectors and testing technicians working in 12-hour shifts were needed for this 36-hour placement duration. One of the interesting items with the concrete coming from 2 different plants was that we had to monitor which pumps those concretes were going to, so we would know exactly where all the concrete that went into the footing was coming from with respect to those plants. Also, with respect to that concrete placement, we had inspectors inspecting not only the concrete itself and that it's passing its tests, but we also had inspectors inspecting the placement procedures to make sure the concrete was placed and consolidated properly. With respect to concrete testing, the Port Authority had what was called a water to cement ratio test. It is a test that you do not see frequently in the construction of highways and bridges in our area. However, they were they were concerned with the water content in the concrete. So every 3rd truck in that placement was tested for air content, for slump, and for the water to cement ratio, because the water cement ratio has a lot to do with the cracking of concrete, and the Port Authority's Materials Division was very concerned that they did not want to have the new bridge develop cracks in the concrete. So that water to cement ratio test, and it's a time consuming test. It generally takes 20 minutes. Sometimes that test was run in the plant to save time when it came out to the field. However, everything went accordingly with that test. And that test was also implemented in the precast plants by our precast inspectors. So that was unique in that usually in precast plants, the precast plant personnel test the concrete and or the different authorities or DOTs. However, on our project, our inspectors were responsible for testing the concrete also. Most of the concrete placements on the project were mass concrete placements, which required thermal curing control and embedded temperature sensors. KSE monitored and tracked the curing temperatures on a daily basis to verify that the internal temperature and temperature differentials were not exceeding their limitations, and to confirm with the contractor when the curing period was completed in order to advance to the next section of towers. Now, a lot of these placements, since they were mass placements, particularly that footing, you can see that when we did the footing, someone might say, well, how did you keep the concrete from overheating due to the mass concrete? Well, what they do is they submit a thermal control plan that a specialty firm puts together. And a lot of our placements had cooling tubes that ran 1 inch, 3/4 inch cooling tubes that ran through our placements at about 4 feet on center. These cooling tubes were connected to a cooling plant, and this cooling plant could control not only the flow of the water but the temperature of the water. And we generally circulated cooling water that was approximately 50 degrees through these pores. What that also did was if you don't have cooling tubes, it takes much longer to meet the thermal control requirements. So that obviously adds time to the project. But with the cooling tubes, it expedites the project to get it done in a timely fashion. I just wanted to explain a couple of these photographs also here. In the center bottom, that's the rebar for the tower pylon leg segment. As you can see, like I said earlier, there are number 11 and 14 bars in there, but we also had rebar bands around the entire perimeter. And then we also had hooks that ran all throughout the tower leg in both the north, south, and east, west directions. In the top right, that was our coffer dam. You can see the drill shaft casings there. When they drilled them, they constructed a drilling platform actually within the coffer dam. In the bottom right photo, what happened was after they would do the drilling of the drill shafts, they would then come in and we had to demuck the entire coffer dam by about 4 to 5 feet. And then that material was properly disposed of through disposal facilities. And it was pretty much loaded on barges and hauled out that way. Then once that was done, we did a 5-foot tremie pour to construct a plug in the coffer dam. And on top of that tremie pour, they poured a second thin lift, which would be the working surface for the top of the footing and then the installation of rebar and things of that sort. Next slide, please. The construction of the towers included fixed platforms for inspection and maintenance above the roadway for security, and the placement of electronic devices regarding the structural health monitoring. The back spans and main spans of the bridge had traveler inspection platforms. And the way you would access these platforms was through a ladder that would either be through the wind fairings or that would be a ship ladder on the side of the bridge with all the safety considerations. And then they would access our fixed platforms in order to access onto the traveler that would then run under the back span and the main span of both bridges. So there were a total of 6 of them. In this slide down below in the middle, you can see the erection of the main structural steel framing girder at the tower pylon. These girders were post-tensioned to the tower pylon through 2-inch diameter PT bars, high-strength bars. Once the girders were erected, the rest of the framing then could proceed out and away from the edge girder towards the center of the midspan and towards Pier 2. As the framing proceeded, KSE inspected every bolted connection to the turn of the nut method with certified structural steel bolting inspectors. KSE created a bolt testing tracking logs to track every connection. Every connection in the bridge was tracked to assure that the 100,000 plus bolts were inspected and properly tightened. KSE utilized our controlled inspection structural steel checklist as a part of this quality requirement and reviewed all of the contractor's QC structural steel checklist for completeness in order to complete the structural steel certifications to allow traffic on the bridge. I'd also like to point out a couple of other things in these photos. In the bottom left, that is the tower footings bottom rebar mat. That rebar mat was composed of number 11 and 14 rebars. The rebars not only had couplers that had to be tested and inspected to assure they were properly connected, but they also had terminator heads at the ends of them, at the ends of the footing, due to the stresses that the entire bridge imparts into that bottom mat. I'd also like to go over to the top right. That formwork is the formwork that creates the core for the hollowed sections in the tower. Those hollow sections, as you can see, were probably 6 feet long by 4 feet wide. So they were tight conditions where ladders and platforms were constructed at the anchor box levels. The false work platform for the construction of the strut is shown in the bottom right. This false work was installed at the top of the tower so that we could construct the platform that was required to support the strut, which was approximately 500 cubic yard placement of concrete. So there was a lot of construction engineering that occurred in this particular project. Next slide, please. In this particular construction of this bridge, we had complicated rebar configurations with PT ducts with the strut tie-in to lift 8. When we first caught a glimpse of the rebar drawings for the strut, for the anchor boxes, which you can see in the bottom center photograph, you can see how all that rebar's in there. It's curved underneath the box. And then we also, in the pier diaphragms, had complicated configurations. So what KSE did was we had suggested to the contractor that they take a look at possibly bringing in the design engineer's field engineer when we did the strut construction, because we knew that there would be issues that would arise that he could resolve on the spot. They did take that recommendation and the engineer came out for the first week of when we constructed the strut rebar, and it was very helpful in resolving field issues that came up. One of the other things that KWM did was they developed an awesome 3D model of the different configurations of complicated rebar, and it was color coded, which really helped during the construction of it. And obviously, once we went through the lessons learned to construct the first strut or the first lift with the anchor boxes or the first pier diaphragm, we were ready to continue with constructing the other ones with obviously the issues resolved. I'd also like to point out that the horizontal, the construction of the towers included post-tensioning and grouting of the back span and the main span bridge deck panels. I spoke about the edge girder erection with the PT bars, and the horizontal strut between the pylons not only connected the pylons through this rebar configuration, but also through tendons for post-tensioning. The strut consisted of 8 tendons, each with 32 strands. Each tendon was stressed with a multi-strand jack to over 200 KSI. KSE's inspectors for post-tensioning operations were certified multi-strand and grouting PT specialists who, during the jacking of the tendons, assured that the jacking pressures were not exceeded and measured and documented the tendon elongations for acceptance. After jacking the tendons were grouted with a specialty cable grout. There was a pre-grouting, pre-activity meeting where we actually made the grout first and tested it to assure that it would meet the requirements of the project, which was very successful in performing the grouting. During the grouting operations, we tested the grout for acceptance with the flow cone for consistency and the mud balance for density. The grout would then be pressure injected through the tendon at a high rate. The tendon had vent hoses at certain locations along the tendon where the inspectors would visually assure that the grout filled the vent hoses before closing the vent hose valves. This would assure the removal of all air voids in the tendon for corrosion protection. Obviously, there were controlled inspection checklists completed for these operations. I wanted to point out a couple of things in this photo too. In the bottom right photo, you can see our cantilever formwork system. We called it the birdhouse. An inside portion of it is shown on the bottom left. This is the bottom level of the birdhouse formwork system by cantilever. And there were 2 other levels. The one above it is where the rebar installation and the formwork installation occurred. And then the top level is where the concrete placement of the tower segment lift occurred. Once we came out of thermal control, this system, this birdhouse, was self-lifting, where you can see in that bottom left that the yellow jacking posts were attached to the tower and actually lifted the entire birdhouse up to the next lift to start the next operation with that. In that bottom area, what would happen is if there were any concrete defects for any reason or any minor cracking, they would then be repaired at that level before it was lifted up, because obviously access on the job was all through man lifts and or cranes. Next slide, please. The construction of the superstructure started on the eastbound bridge first. since it was not affected by the existing bridge's alignment. Construction of the superstructure required a large bridge erection manual that included structural steel framing, erection, lightweight precast concrete panels that were manufactured off-site, obviously, stay cable installation, post-tensioning, wind fairings in their baffles for the wind loading on the bridge, and jacking Pier 3 shoreward to set the fixed bridge bearings at Pier 3. Each bridge had a bridge erection manual with many stages, sequence, and steps that KSE monitored daily to assure the contractor adhered to the right steps at the right time. There were real-time engineer of record approved changes to the eastbound bridge erection manual, and obviously lessons learned that were incorporated into the westbound bridges erection manual, further expediting construction of the westbound bridge. What I wanted to point out in these particular photos was obviously in the top right, you could see as the bridge approached the midspan to make that connection. What was very interesting was that templates were made and shipped down to the structural steel fabricator Canham. They then drilled holes into the main girders, and those girders were then shipped up to the project. This was integral into the successful mating of the bridge at the center of the midspan. Also, you can see the cantilevered construction method in the bottom left, where the backspan was supported on false work and the midspan was supported through the stay cable system. In the center photograph, there again is the edge girders that were post-tension to the tower. But what was also interesting was the post-tensioning bars. They helped connect the girders to the towers, but in order to prevent sliding and to further stabilize the edge girders at the tower, the Canham fabricators, the edge girder had a base plate that bared on the vertical tower concrete. This base plate had bars welded to it to form a shear key. So when that edge girder came up to the job, they all had bars, but the contractors, carpenters, had to construct a template or a form. So when we placed that tower segment and they stripped the forms, the keys for the bars were there. All right, and that helped stabilize that edge girder, not only to have it vertically attached to the tower, but to prevent any sliding from bridge loading during construction of the edge girders. I wanted to point out the other thing with the wind fairings and the baffles. Obviously, the bridge had to go through a wind loading exercise at one of the few companies in the world that specialize in bridges and wind loading. After that exercise took place, it was determined that the bridge was going to have wind fairings. And wind fairings are like, if you look at an airplane wing, the way the front of the wing is curved, it's the same idea. They got mounted on the south fascia of the eastbound bridge and the north fascia of the westbound bridge, particularly in the main span. What would happen is as the wind approached the bridge, that would redirect the wind over the bridge and under the bridge, but vortexes could occur under the bridge. So baffle plates, which were vertical plates, were installed into the steel framing to prevent those vortexes from causing any problems with the bridge's structural integrity. Next slide, please. Okay, so the lightweight precast panels, they were made off-site. They had stainless steel rebar in them, and they had to be lightweight for the design of the bridge. And they were checked to make sure that they fell into the parameters of the weights that they had to have, as you can see listed here. They were 7,000 PSI, and they weighed about 125 pounds per cubic foot. The stainless steel reinforcement, as I mentioned, was in the panels, but it was also in the field installation. So you can see that what would happen with the construction of the bridge is in the bottom right, you had the steel framing. On the bottom left, they would fly in the panel, and this panel would sit about 2 inches on the framing around the perimeter of the framing on blocks, on plastic blocks. Then they would come in and they would stitch in this stainless steel reinforcement. And everybody knows that stainless steel reinforcement has dissimilar materials issues. So one of the things that KSE inspectors did was they made sure that that stainless steel was properly supported either on plastic chairs or with existing stainless steel that was coming out of the ends of the precast panels, as you can see that those 180-degree hooks do. The post-tensioning at Pier 2 and midspan decks, we talked a little bit about. Those decks pretty much had 4 strands per tendon, and the tendons were in different lengths in the main span. And the PC wearing course we'll talk about in the next slide. I did mention earlier that, you know, all of our precast had the QA checklist in the plant for inspection, and they were filled out, adding to the hundreds and hundreds of checklists we had for this project that really assured an extra level of quality into the project. The project was unique in that it had an extensive crack mapping requirement included in the contract by the Port Authority. I mentioned earlier the Port Authority's concern with cracking in the water to cement ratio. Every bridge concrete placement required 3 stages of crack mapping. One when the concrete curing was completed, one after the full dead load was placed on the bridge, and one at least 7 days after the live load was placed on the bridge. The contractor performed the crack mapping with KSC's inspectors either witnessing the mapping or verifying the mappings were correct soon after they were performed. KSC also created crack mapping tracking logs to assure every placement was mapped for each of the 3 stages. There are over 2,400 crack maps created for the project. And what was interesting also is that since there were 3 maps, if any cracks were found in the first or second stage of crack mapping, you could see whether they grew in length or width in size of crack thickness during this exercise in mapping the bridge. There were some minor cracks that were developed in the bridge that were eventually repaired as per the crack repair specification. With that, next slide, please. Okay, in this particular one, I talked earlier about the post-tensioning of the back span and the main spans. The Pier 3 expansion joints and bearing setting was a very interesting procedure that was in the bridge erection plan. Since the bridge only had 2 expansion joints above Pier 3, right? And the less expansion joints in the bridge, the longer the bridges last. So at Pier 3, it was very interesting in that the main framing for the bridge was connected to the pier cap through fixed bearings, okay? And the precast girders that came in from the approach span, they bared on the top of the Pier 3 pier cap on expansion bearings. So the expansion took place, you know, through the precast approach spanned girders. As part of the erection manual, what we had to do was, when we went to set the fixed bearings, we had to actually jack the entire pier cap shoreward approximately 2 inches to set these bearings, depending on what the temperature was that day. And it was a very unique operation that I, for one, have never seen before. The bridge also had a pedestrian walkway. You can see in the bottom right photograph, that was the construction of the deck. And to the right of it, there should be the pedestrian walkway. The westbound bridge had the walkway. You can kind of see the walkway in the center photograph where the stay cables came down into the deck. The walkway was on the opposite side of the stay cables. One of the really great quality features of the bridge deck is the polyester polymer concrete overlay. The construction of the bridge deck consisted of 2,000 linear feet of the polyester polymer concrete. We called it the PPC 1-inch overlay between New Jersey and New York Pier 2. KSE was fortunate to visit the K Bridge in Brooklyn, where the contractor subcontractor was constructing the same overlay as proposed for Goethals Bridge. KSE observed the preparation and placement of the overlay on the eastbound K Bridge and was able to discuss quality requirements with the subcontractor and the K Bridge inspectors. This was quite helpful for our inspectors' knowledge and acclimation to the operation. It also was instrumental in developing the controlled inspection checklist for this operation, since we were tasked with developing all of these checklists based on the specifications and the contract documents. And like I said earlier, the EOR chimed in and would typically add items to the checklist because he certified those checklists. Once the operation came to the Goethals eastbound bridge, KSE was fully prepared to monitor, observe bond testing between the overlay and substrates, and to inspect the operation with the controlled inspection checklist. The subcontractor that constructed the overlay, it's a very interesting organization. They go around the country to different bridges to construct these overlays. They plan this work very well because everything, all the material, all the chemicals, all the equipment, everything utilized to construct this overlay is transported to the job. And once it is all scheduled and on the job, then the subcontractor comes in with his labor and equipment and constructs the overlay for the bridge deck. The bridge deck is a chemical overlay. It's it cures probably within 30 minutes. You could drive on it. It's very strong and durable, and it's really going to last quite a while for the Port Authority on these two bridge decks. With that, the next slide is going to be a video. It's going to take you through the single cantilever construction method. So as you can see, during this method of the single cantilever construction, It was utilized at each tower to erect the bridge and join it in the mid-span. The back spans were supported on falsework, as I said earlier, while the main span was supported through the stay cable system and the steel framing. What was interesting was that as the bridge was constructed, in the back span, we would actually have lift off of the pedestal supports that were then removed as necessary to construct the bridge. You can see that it went very well. Another thing too that I wanted to talk about a little bit before we get to stay cables is that in stay cable construction, it's very easy. It's more conducive to raise the bridge, okay? Because as you raise the bridge, the strands are pulled, okay? And when you pull these strands, you do not want to go back into areas where there could be wedge biting and things of that sort. So, you know, very rarely, it would be very complicated if you over raise the bridge. So when they constructed the bridge, it was lower than when they met at midspan, and in some instances, several feet lower one side than the other. But with the stressing of the stages of stay cable, they were able to bring the bridges up to the proper elevation to construct it in the middle. And with that, we're going to go into the next slide for the stay cables. So the construction of the stay cables for the two bridges included 5 stages of stressing with surveys as per the bridge erection manual. There were 18 stay cables per tower pylon with 30 to 65 strands per stay cable, depending on the length of the cable, with the longest stay cables being over 425 feet in length. There are over 60 miles of strand in the bridge's stay cable system. When I was talking earlier about how they lift the bridge to join it in the middle, they also had to do some horizontal steering with steel cables and come-alongs, because as the bridge extended out horizontally to meet in the middle, it could vary to the north or south of the bridge. And the steering was to bring that back into alignment. And like I said, you know, it went very successfully with the joining of the bridge, which is always, you know, the biggest concern in the construction of bridges of this sort. The counterweight at Pier 2 counters the main span loading through the stay cable system. The counterweight is at 200 cubic yard mass concrete placement on the top of Pier 2, encasing the main structural steel framing where the last 3 stay cable deck anchors are located. You can see in the center picture that the crane that is to the left side of the picture is a Liebherr 1500. These cranes were basically integral in constructing the bridge. Most of all of the concrete placements were through a concrete bucket lifted by these cranes, and they were really successful in constructing the bridge. Not only that, we had trestles constructed, so the cranes would bear on the trestles, and the trestles would handle the loading of the crane and whatever different materials it was lifting. You can also see in the bottom left photo that the traffic is on the one westbound bridge, while the eastbound bridge is under construction. I think it was in the overlay work. With that, we'll go to the next slide. In this slide, this is the general layout of the stay cable. Fresnay is the supplier of all the stay cable materials and installation equipment, and provided what's called ITPs, inspection and test plans for quality control. Each minor operation to construct the stay cables typically had an ITP. KSE subconsultant KPFF, they developed both the furnishing and installation stay cable controlled inspection checklist, which covered fabrication through installation and testing. We did visit the quality control departments of the wire manufacturer and also of the manufacturer that put the HDPE sheathing on the cable. In addition, KPFF, they reviewed all the ITPs for completeness, and they also made sure that they conformed to the contract documents and provided oversight for the whole operation. In the bottom right is what the strand looks like. There's 6 outer wires and a king wire. The reason they call it the king wire is because it's the center wire, but that particular wire is also stripped to play an integral part in getting the stay cable strands into the tower anchorages and the deck anchorages. And then may I go to the next slide, please? In this particular slide, I wanted to go through the bullets real quick first. So like I said earlier, this king wire, what they do is for temporary corrosion protection, this is a critical function in the stay cable installation. The strands are cut to length off of large spools on a cutting table, which is shown in the center photograph. Both ends of each strand then have the HDPE sheathing removed for several feet in order to insert the ends through the stay cable, through the tower and deck anchorages, where the wedges in the anchorages grip the strands. Once the sheathing is removed, the KSE inspector is assured that the ends are completely coated by hand with a cable wax to provide for temporary corrosion protection. The strands are then hoisted in pairs for the installation into the anchorages as seen in the bottom right photograph. That is the hoisting where they're lifted up and inserted in pairs into the anchorages in the tower and then down into the anchorages at the deck level. Pattern templates are located in both the tower and deck anchorages to ensure the right numbered cable is inserted into the right numbered hole and the anchorages to avoid intertwining of any strand. You can see in this bottom left photograph how the strands all run adjacent and parallel to each other. So in stay cable construction, there can't be any intertwining because it causes problems with the stay cable and fatigue. KSE monitors this strand installation full-time to confirm intertwining does not occur. The bottom left photograph shows installed strands that I said earlier parallel to each other and not intertwined. That pretty much covers this slide. With that, we may move to the next slide, please. Damper installation. Stay cables are susceptible to vibration from wind loading that can cause fatigue in the strands. To suppress these vibrations, internal hydraulic dampers are installed around the strands of each stay cable near the deck anchorage. The compacting collar you can see in the bottom left corner, that the black band is the bladder. The collars themselves are these aluminum or stainless steel collars. The complete unit's called the half piston installation. After the bladder is installed around the strands near the deck anchorage, that's where they're located, KSE inspects the injection of hydraulic oil to the specified pressures for each damper. Once that's done, a company, a specialty testing company comes in to determine the dampening results, which are then reviewed by the engineer of record for acceptance. Once they're accepted, they can then lower the vandalism tubes down underneath the dampers, and you can see one of the dampers that's installed in the bottom right photograph. Next slide, please. Finishing work basically consists of cutting the strands to the required length to fit in the stuffing boxes and the anchorage caps. Over blocking the wedges is really setting the wedges, because the anchorage then gets bolted down, which locks the wedges in for permanent construction. Then there's the closing of the anchorage boxes and the wax injected. In this slide, you can also see the monostrand jack being used to stress the strands. As I said earlier, each strand could be stressed up to 5 different stages. The monostrand jack is connected to a field computer to control stressing and elongations and document technical parameters of the strands. The elongations are also field measured and documented. This information is sent to the engineer of record for analysis and to determine the next stage's stressing requirements. The mono jack, you can barely see it in the bottom of the photograph to the left, but then you can also see the workers working with it in the photograph to the right. At the final completion of strand stressing, finishing work proceeds to complete the anchorage system, both in the tower and at the deck. With respect to corrosion protection, those exposed and waxed ends I discussed earlier, the strands, are now cut to close the stuffing box. Wax is then injected into the anchorage and the stuffing box, and you can see what the wax looks like, how it encompasses the strands coming out of the anchorage. So what KSE does is we monitor that wax injection to assure not only does the temperature of the wax is within the acceptable limits that it needs to be for it's probably about 180 degrees, give or take 5 degrees. But not only that we check for that limit, but we also check, more importantly, that the wax exits the vent holes in the anchorages, assuring that there's no air voids in the anchorage and provides for permanent corrosion control. With that, I will turn it back over to James, and thank you.
Thank you, Scott, and thank you, Rasul.
Thank you.
Now we're going to go into a short segment of our assessment for learning, which has approximately 10 questions that will cover some of the topics that we spoke about on this morning's presentation. First question: when was the original Goethals Bridge constructed and opened? (1928). Second question: give one reason why the Goethals Bridge had to be replaced. And there was many reasons that were presented in the presentation, but for this question, we were just looking for one. Functionally obsolete, lack of shoulders, no pedestrian or bike lanes, and only 2 substandard lanes of traffic. Question number 3. Name 2 of the roles or responsibilities of the construction engineering and inspection firm, KS Engineers. Controlled inspection checklist, quality assurance inspections, certification of results, punch list, daily work reports, non-conformance reports, to name a few. What type of foundation system was utilized on this project? Drill shafts and piles. As Scott mentioned in his presentation, what are the 2 unique features of the towers? They were poured in 17 lifts. They were hollow at the top portion. There was a 5-degree outward lean, as Scott mentioned. There was cladding at lift 10, and they held approximately 45 to 110 cubic yards of concrete per lift. What is the main span deck wearing surface? And we just spoke about that. PPC or 1-inch polyester polymer concrete. This one, how many stay cables did we have per structure? I think we had to do a little bit of math for this one, but 72. Why was it necessary to replace the Travis Spur Rail Bridge, which was the bridge over in Staten Island that we had to replace over a long weekend? Because of the expanded I-278 roadway width, we had to be able to fit that roadway underneath the bridge. Did the CEI perform quality control or quality assurance? And I spoke about that in my part of the presentation. Quality assurance, amongst other things. And the last question, what project delivery method did the Port Authority of New York and New Jersey utilize for this project? Public-private partnership. So that ends the questions, the assessment of learning questions that we have for this presentation. And I'm going to turn it back over to John because we only have 10 minutes left to see if he has any questions from any of the participants.
Hey everyone, there are currently no questions. If anybody has any questions, please feel free to throw them into the Q&A down the bottom there, and we can answer them right away since we have a few minutes left here.
Okay. John, I have a couple of questions, and these might be better suited answered by Scott. Just some detailed questions that we didn't have time to answer during the presentation. And this question would be for Scott. Oh, wait, I see a question. So let me get the audience questions first.
Yeah, that is, what was the total cost of the work?
Rasul, would you like to answer that one?
Yes, it was $980 million, but for the acquisition of the land as well as the maintenance of the bridge, it would add up to $1.5 billion.
Okay, thank you, Rasul. I don't see any other questions. So Scott, let me ask you this. What does the PPC overlay construction consist of?
Well, generally it consists of a chemical binder that is composed of many different chemicals. When they were getting ready to do that operation on Goethals Bridge, we had to get submittals of every one of the chemicals because the Port Authority's MEU wanted to have samples of them, whether they tested them or not. So when we started up that operation, we took care of the submittal ends of it. Then there was aggregate, there was sand, there was some minor stone in the mix. It was less than a 3/8 inch stone. When, like I said earlier, the subcontractor came to the job, everything they needed was on the job. They used a concrete mixer that's similar to what we see. The truck comes out, it's and everything is dry in the truck, and then it is mixed in the truck right there on site. So their mixers mixed right on site, and there were parameters that we had to make sure that they adhered to, and not only that, that their trucks were certified, that they were in good working condition. That mix would then be placed in a typical to an asphalt paving machine, which was really interesting because you know, it came out very nicely in its 1 1/8 inch lift, and that paver pretty much also compacted that mix, so there was no rollers like you see with asphalt construction, and that pretty much is what it consisted of to get it from its dry ingredients and chemicals into an actual overlay on the bridge.
Okay, thank you, Scott. And I think we have another question from one of the participants, and I'm going to try to let Rasul answer. How much does the bridge sway? I guess they're looking for any type of movement on the bridge. How much, Rasul, do we have any answer to that? How much does the
I
bridge
do not
sway?
know exactly, but I would say not more than 1 inch.
Scott, do you have any more to add on that?
Well, I do know for a fact that it moves, because when we're out there and we completed the bridge, you could feel it. Nothing like the Verrazano Bridge, though. Subtle movements. The expansion and contraction at Pier 3, I think, could be upwards of 6 to 8 inches at those particular piers, because those are where the expansion joints are. But it does subtly move, and you can feel it when you're out there parked in your car or standing there.
I have another question, and this is probably for Rasul and for Scott. The question is, what type of concrete mix was used for the bridge piers? And it says allowing it to accept live loads after a short construction duration. And
It was actually for pier column was basically we used 12 different types of concrete mix design for the whole entire project, starting from 4,000 psi all the way to 10,000 psi. Of course, because of all the chemical and admixture inside all the mix design, we would get basically from 6,000 psi all the way to upward of 19,000 psi. For every concrete that we place on this entire project.
Okay, thank you, Rasul. John, I think I don't see any other questions. I want to turn it back over to you if you want to have some closing remarks, since there's five minutes to 11.
We're all good here. If anyone has any more questions, please feel free to throw them in there. If not, as you can see there, you can contact James if you do have additional questions. Other than that, that is going to wrap this up. We'd like to thank everybody for coming out. Thanks to all of our presenters. Thanks, James. Thanks, Joe. Thanks, Rasul and Scott. Really appreciate your time. Hold on, we got one more question. How established affirmative aircraft control to avoid collision seems to relate to human choice? How was, yeah, seems like.
So that's an interesting question. I'm going to try to tackle it and see if maybe Scott can jump in. This seems to be more of a Newark Airport pilot issue. I mean, the fact that the bridge has a set height and the fact that the bridge is lighted with a lighting system would seem to help avoid collisions. But I believe this would be more toward the Newark Liberty Airport control tower and the airplane pilots more so than the bridge construction. But I'll let Scott and Rasul chime in too.
So the bridge has aviation lights on the top of each tower, as you can see in this photograph. We had both temporary lights during construction and the permanent lighting that was installed after the towers were completed. The flight patterns of the bridge pretty much had the planes flying in over the New Jersey towers or on either side of them, depending on the wind conditions at the airport. It's very interesting that obviously the planes can't go below a certain flight deck, which is built into the construction of the bridge and general aviation rules and regulations for that. It's amazing that that the planes steer clear of not only this bridge but just about any other type of bridge that may be near an airport in this country.